All right, this will be my explanation of all the textbook stuff for MAT137. I guess it'd be Unit 14. So right now I just finished Power and Taylor series, 9.1 though, which is just Power series, and I'll just basically summarize everything I learned. Hopefully, it'll console the information for me and act as good review for later. First, what is a Power series exactly? So Power series. Oh, and by the way, I'll go through all of the different examples in the book here, and I'll explain everything that I feel like needs to be explained. The textbook does go into quite a bit of depth that the course probably wouldn't, but there is some useful stuff in here. So, what is a power series exactly? Power series is basically any infinite series in the form of this. So we have the infinite sum from, let's say n is equal to 0, of some arbitrary sequence centered at A for some polynomial. And this is basically what a power series is. A is some real number, and an, I guess an is kind of confusing. I'll use Cn. Cn is some sequence. Right? So this is essentially what a power series is. And x is a variable that we don't know. It's an arbitrary variable. And what we can do with power series, and I'll show why this is important later. Right now, this is kind of just like the broad view. Why this is what we can do with this is determine when this guy is convergent, right? And because we know that the infinite sum of Cn can be convergent, right? And now what if we added some, like if we substantiate x, or instantiate x with something, right? If we use 2, like 2 minus a to the n, this could also be convergent, or it could not be. We don't know. So what we call this, right, we would agree that for different values of x, this could be convergent. For a good example, let's take Cn was equal to 1 over n squared, right? Or actually, let's say 1 over n, right? And let's say a was 0, so it's just xn, right? You would agree that this converges and diverges for a lot of different values, right? Let's say we wanted to use 1. Let's just have x is equal to 1, right? If we have x is equal to 1, then we have this sum, and this is obviously divergent. Now, on the contrary, if we had x is equal to negative 1, right, then we end up with this series, next, and this is just the harmonic series, right, alternating harmonic series, which we know is convergent by alternating series test. This guy goes to 0 as n goes to infinity. He's also decreasing, and he's also always positive, right? Alternating series test, bro is convergent, right? So we can see that there's different values for which this is convergent. And what we call these values of x, right? We know that these values of x must be centered at A, on some interval around A. So if we have a number line, and this is A, we know that there is some interval centered at A where this is convergent. And we agree that when x is literally A, right, this cancels out to 0, and then this whole thing cancels out to 0, meaning that's convergent because it's just 0, right? The infinite sum of 0 is 0, which is convergent, right? So we know that it's an interval centered at A that includes A, right? For the rest of the power series, no, it's centered at A, but to make things a bit more simple, I'm going to rewrite it as just x to n and assume A is equal to 0. All right, this won't change anything because you can just do the exact same things for everything else, but plugging in A, right? A just kind of makes it more confusing. We'll just do 0. So we know it must be convergent at 0, but it can also be convergent for points outside of 0, right? It could or could not be. This, let's say it's up to here. We call this R, we call this negative R. We call R the radius of convergence. And this is pretty important because this is what allows us to figure out when a power series is convergent versus divergent. Now, one key point is at these endpoints, at literally x is equal to r, we don't know, right? It could be convergent or it could be divergent, but everything within negative r to r, right? Everything in here is absolutely convergent, and everything outside, right, over here is all divergent. It's just at these endpoints, it could be both. It could be either. It could be convergent or it could be divergent. And like what I showed you before, if we had this series of 1 over n times x to n, this is a very good example where at one endpoint it's divergent, right? When we know this is true for all x less than 1, right? Or I'll show you why. Let's take the limit as n goes infinity, right? This is the ratio test. We have x to the n plus 1 over n plus 1, right? This is the plus 1 term. And we divide this by just the 1 term, right? So this is the same as like ak plus 1 over ak, right? This is what we're doing here. And we see this simplifies to x times n over n plus 1, right? The limit as n goes to infinity, right? This guy cancels out, and we know this is convergent when this is less than 1. This is the ratio test, right? So we know the radius of convergence is when x is less than 1. Great. But we saw that when x is equal to 1, right, this is divergent. Whereas when x was equal to negative 1, this was convergent, right? This is the alternating series test, right? So we know the radius of convergence would be negative 1 to 1, not inclusive. Radius of convergence. There you go. Let's see what other content. I'll omit the proof, because I kind of think the proof is kind of dumb. Like, I don't know. It's kind of dumb. I don't know. But I will show you this example. Do this on your own. And all right. Wait, backtrack. Quick notation jargon thing. This is called the domain of convergence, whereas this is the radius of convergence. All right, different things, right? This is also called the interval of convergence. So domain of convergence, so domain / interval of convergence, whereas this is just the radius of convergence. All right, that's just a quick okay, yeah, not that important, but I don't know, maybe there'll be a trick question, I don't know. But here's the example. Let's find both the radius and interval of convergence for this series. X to n over n squared to the n. All right, try to do it at home. But and I'll just go through the answer. What we want to do here is use a ratio test. All right, so we have the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 squared times 2 to the n plus 1, right? We divide this by just the normal term. Oops. Right, and we know this is equal to the limit as n goes to infinity of absolute value of x. These two cancel out to just 1 over 2, and we have n squared over n plus 1 squared. These cancel out to 1, right? And we know all of this has to be less than 1. So we know that the absolute value of x over 2 has to be less than 1, meaning the absolute value of x has to be less than 2, meaning x can be in between 2 and negative 2. So our radius of convergence is equal to 2, okay? But our interval of convergence, we have to figure that out. So we have to plug in, or this is our series, right? We have to plug in when x is equal to 2 and when x is equal to negative 2. Because at these endpoints, we don't know whether they're convergent or divergent. We only know that in between these values, it is convergent. So to find our interval of convergence, let's plug in x equals 2, and this we end up getting n equals 1 of this would be 2 to the n over 2n times 2 to the n, right? And this is just this 1 over n squared, which is absolutely convergent, right? So we can include this point, right? Now at x equals -2, we end up getting -2 to the n over n squared times 2 to the n. This simplifies to -1 to the n times, so it'd be 2 to the n over 2 to the n, which cancels to 1, times 1 over n squared. And this is also convergent, right? Because, you know, if 1 over n squared is convergent, absolutely convergent, right? And this also has to be convergent. Great. So now we know the interval convergence is -2, 2. Awesome. That's power series. All right, not too bad. There's a few more examples. Okay, you can skip this part if you think you're comfortable with this, but I'll present a few things that I thought were pretty cool from the textbook. And one of them is this proposition, where we know for any series, let's write it like this. For any series like this, all right, we know the radius of convergence, we'll denote it as r, is equal to the limit as n goes to infinity of ck over ck plus 1. This is the theorem. Like I said, it's just this. And it's pretty cool. Okay, so we'll see sub k is just some, like, you know, if we did it with, let's do it with this. I'll just quickly do it with this example to show that I'm not crazy. And is equal to 1, 6 n to the n. I'll just use k. The book uses k, and I'm trying to, I don't have anything against k, so I don't know why I'm not using k. X minus 2 to the k, right? Now, what we could do is just ratio test this guy, right? But honestly, what's faster, since we know in this case c sub k is just this term, right? Because we ignored this. So we take the limit, so n goes to infinity, of ck, this k, oh my god, why is it n? Well, k, right? Divided by c sub k plus 1. So this is k plus 1 over 6 to the k plus 1. We get rid of these absolute values because these are all positive terms, right? And we end up getting, this cancels out to 1, and this cancels out to just 6. So it goes 1 over 6. So we know the radius of convergence is literally 1 over 6. Okay? But the radius of convergence, right, since it's centered at 2, then we know the interval of convergence, before checking the endpoints, is x minus 2 less than 1 over 6, right? And this ends up being 11 over 6 to 13 over 6. And now checking the endpoints, right? If we check the endpoints, so this will be when x is equal to 13 over 6. So, sorry, backtracking. The point of this is that this is just like a very, I mean, it's just an extension of, what's it called? Ratio test. But in my opinion, it makes it a bit easier because you don't have to worry about the x term. I mean, you still end up using it. It's like basically the same thing. But I find it pretty useful. By the way, doing this example, right? You can do the rest on your own, but I'll just go through it right now. This would be k plus 1. And if we have 6 to the k over k, 13 over 6 minus 2 is 1 over 6 to the k. This cancels out to 1. And we know this dog, right, is divergent. So he's divergent. Now when x is equal to 11 over 6, we see that this series, it becomes -1 over 6, right? Because 11 over 6 minus 2 is -1 over 6. You can also plug these guys in, right? Like, This is why I like seeing this, because this gives you the exact radius convergence centered at 2, right? 2, and this is 2 plus 1 over 6, and then this is 2 minus 1 over 6. So when you plug this in, right, it'll cancel it with this 2 anyway. So you can just plug in negative 1 over 6 and 1 over 6. And this, we get 6 to the k over k times, we can factor out the negative 1 to just get 1 over 6k, right? These guys cancel out. And now we get, again, our alternating harmonic series, which we know is convergent, right? Meaning our interval of convergence, or domain of convergence, includes negative 11 over 6, but doesn't include 13 over 6, right? Now, lastly, this is the last theorem I want to cover before moving on to power series as functions, is the root test. The root test you should be familiar with, but I think this one's pretty cool as well. So again, we'll take this series. Let's denote little r, or no, let's say 1 over big R, right, where r is the radius of convergence. This is equal to the limit, as n goes to infinity, of the absolute value of c sub k to the 1 over k, right? And when this is 0, if equals 0, then r is equal to infinity, okay? Whereas if equals infinity, then r is equal to 0, okay? This is what the test says. Now let's use this for example. You can do this for yourself, negative 3k, x to the k over k 2k. Use this test and see what you see. I'll do it real quick. So we can get rid of this term, right? We don't care about the x to the k, because we just care about c sub k. So if we take the limit as n goes to infinity, k, I keep on using n, bro. K goes to infinity of negative 3 to the k over k to the k to the 1 over k. All right, since this is all absolute valued, right, we can get rid of absolute value and get rid of this negative. All right, no one cares about the negative. And now all of this is to the 1 over k. So using exponent rules, right, this top just becomes 3, and this bottom becomes k to squared, right? And this is equal to 0, meaning our radius of convergence is equal to infinity, meaning our interval of convergence is just the real numbers. Pretty cool, eh? Because you wouldn't really be able to see that based on just this, right? Like maybe you could, but I don't know. But yeah, that's the root test for interval convergence. I think it's that this one's more useful than the other one, because the other one's just an extension of ratio tests. It's kind of obvious, but this one's pretty cool. Yeah, moving forward, next section. We want to write power series now as functions, because we saw a power series, right? A power series is like this, right? And we see that it's a function of x. So it's very obvious to denote this as a function, right? And this works. This is valid, because this whole infinite series depends upon x. And now we see something a bit more subtle. We don't know what happens. No, we know this. We know this diverges, meaning it doesn't exist when outside of its interval convergence, right? Now let's say its interval convergence is let's say interval convergence is a minus r to a plus r, right? Then this function is defined only on this interval, and we produce like a real number, right? I mean, yeah. This is the little subtle nuance that we got here, a bit of nuance. Because outside of this interval, right, we cannot say it exists. This function is defined because this does not exist outside of its interval convergence, right? Because if we were to graph this, right, if we were to graph f, on a function of x, right? It might look like this. And then say this is the interval convergence. And then over here, it might be like, I don't know, like a cat, right? It doesn't exist over here. We don't know what happens out here. It's divergent, right? It could be an elephant. It could be a cat. Like, okay, probably not, but the point is it doesn't exist outside of interval convergence. So these functions are only defined on this interval, right? It's not even that they're asymptoted at those intervals. No, they don't exist outside of it. All right, so that's a very key point, because these functions might only exist at a single point at 0, right? Or they might go like this. And another nuance is that if we have centered at A, right? What at f at A, right, is always gonna be equal to 0, right? Because the infinite sum of anything times 0 is 0. Okay, I think. Take that with a grain of salt. It doesn't say that in the textbook, but I'm pretty sure that's true. Yeah. Okay. Moving forward. Let's see what I gotta cover. I gotta cover. Okay, and now another nuance. I'll omit the proof, because the proofs in the textbook are honestly kind of stupid. Like, it's like there is so dense, and there's like different symbols that I've never seen before. Like, there's density symbol in here. I'm guessing it's not for density. That'd be kind of misplaced, but okay, key point. On this interval, right? F is actually continuous. This should make sense, right? As you increment x, this series can't just like sporadically jump, right? This should make sense, right? And another nuance. This is it's called Abel's theorem. I want to make this a bit more general, right? Let's say we have some radius convergence R, and we centered at some interval A. Okay, then what we have is for any function convergent on this interval, right? We know the limit as x goes to a plus r from the left is equal blah blah blah. Okay, I'll just write it out. I'm being lazy right now. I'll just write it out. So k is equal to 0 of ck rk. All right, this is what it's saying. Basically, what it's saying. This is I think this comes from the corollary that this function is continuous on that interval. So this should make sense, right? Basically, it's just continuous on this interval, so you end up getting this, right? Even they omitted the proof, so I don't even want to touch that. But okay, the main point of that is that the function is the continuous on this. Okay? Now, this is where we get a bit more nuanced. Okay? Or sorry, it gets more interesting. Okay. Now we know we can write this infinite sum. Okay, let's just take like this sum, right? We can write this as 1 plus x squared plus x cubed plus blah blah blah, right? Would you agree that all of these are polynomials, right? Okay, they're all polynomials, obviously. What can you do with polynomials? So we know Alfonso said that we can treat polynomials are, what did he say? Like nice. Polynomials are nice, but why? I don't really understand why, but it's kind of obvious now in hindsight. We can differentiate this bad boy, all right? Because each term you can differentiate on its own, right? So that's why we can actually take, so this is f at x, right? We can actually take the derivative of f at x, which is the derivative of this sum. And we can literally just like work it in here, this straight up. We can just be like, all right, this is k, x to the k minus 1. Now, why is this the case? Well, we can see, we can just differentiate each one of these terms, right? This is 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus blah, 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 right? And we see this is literally equal to this, right? Just straight up. And on the contrary, we can also integrate this bad boy. All right, we can integrate this guy. And so we can actually get the integral of this guy, right? Which is the integral of 1 plus x squared. Like, we got an infinite integral. Sorry, these are all, you have to write dx at the end, dx. And the way we do that, we can literally just like work in the integral into x to the k. So we actually end up just getting xk plus 1 over k plus 1. It's so wacky, but it makes sense, right? If we integrate this, where we end up getting x plus x squared over 2 plus x cubed over 3 plus, right? And we see this is equal to that. Pretty cool. Oh, yeah, and you have to add a plus c, obviously, because, you know, that's 8 marks right there, right? You got to add a plus c. Not on this side, sorry. On this side. And the way you figure out the plus c, so you know... I'll give you an example later, and I'll show you. But basically, that's what you can do. And moreover, we know f has some interval convergence, right? Or so some radius of convergence. The radii of convergence for this and the when you differentiate it is also it's also the same. So say this has radius convergence r up here. This also has radius of convergence r. The only difference is that at the endpoints, it could be different. So the endpoints are like they misbehave, right? And I'll give you an example of a power series whose what's it called, interval convergence are different between itself and its differentiate itself. So let's take this function. We'll have them as this. K equals 1 of -1. Sorry, I'm copying from the textbook because they have good examples. Okay, and now let's differentiate this bastard, right? So this guy becomes... okay, so differentiating this guy, we ignore all the non-x terms, and we just differentiate this guy, right? And then these k's cancel out, and we're left with just this. Okay, this guy, let's determine his interval of convergence, yeah? So we know, let's use, what test should we use? Let's use, let's just use ratio test. Ratio test is very, very, what's it called? Consistent. Okay, so we have our absolute values, and we have k plus just k, and then we have xk, -1 to the k. Since it's absolute values, -1s become 1s, right? And then now we're left with absolute value of x, right? Because the k's cancel out, times k over k plus 1. All this has to be less than 1. This cancels out the 1. So we know the interval of convergence is x between 1 and 1, -1. And now at x equals 1, right, we are left with this, -1 to the k over k, and this is convergent. This is just the harmonic series. Now, at x equals -1, we have this, and we see this becomes -1 to the 2k over k. The 2k is always even, right? This is always an even number. So this guy gets decimated into just 1, all right? And this is divergent because this is just, integral test, blah, blah, blah. So we know the interval convergence of this one is -1 to 1. Great. Now this guy, let's do the exact same thing. Let's take the ratio test. All right, -1 k plus 1 over x to the k. When we divide this by just a normal term. Oh, sorry. Hold on. I messed up. -1 k plus 1 x to the k over -1 k x to the k minus 1. And this ends up just being absolute value of x, right? And this is all less than 1. This is the ratio test. So we also get the same interval convergence. Oh, sorry. We get the same radius of convergence, right? There's no proof for it, but I don't even understand the proof. I don't think we have to understand the proof. Just take my word for it. I'm sure there's an easier way to explain why. I mean, it kind of tracks, right? Like it makes it. I don't doubt it, right? But anyway, let's figure out the interval of convergence now. So at x equals 1, we see that this infinite sum becomes -1 to the k times 1. And this is divergent. And then at x equals -1, we have this, which is equal to this, which is also divergent. If the series of some finite number is always just divergent, right? So the interval convergence of this is actually different. See? Different. It's different. Yeah, I don't tell you, it's just different. And let's see, what else do I have to cover? Okay, and some quick housekeeping items to cover. We know, okay, so let's have some function f of x like this. Right, ck x minus a x k. On its interval of convergence, on this interval of convergence, we know it's differentiable. Or on the closed brackets. On this, all right? Sorry, hold on. On this bad boy, this guy is differentiable and integral. It's integral because it's continuous, right? And it's differentiable just because it is. The proof is a proof, right? But it is. It should kind of make sense, right? I think it kind of makes sense. And lastly, integrable. Okay, yeah. Great, yeah. And now let's do some examples of applications because I think this is where it's the most important, right? Let's take a look at this example. So we just covered, all right, to conclude, what did we just cover? All right, we just covered what a power series is, right? And it's just some infinite sum, right, of something that looks like this. All right, that's what a power series is. And since x is some independent variable, we can represent this in respect to some function. This is what we've been doing, right? And of this, we can figure out its interval convergence by using ratio tests to figure out what x's work, right? And we also determine that on its radius of convergence, the interval given by its radius of convergence, right? Home dog is both differentiable and continuous. All right, that's what we know. That's all we know right now, and we can perform differentiation and integration on this guy just as if this sum just didn't exist, like if it was just like normal, and then you put the sum in after. All right, this is what we know so far. Only thing you be careful with integration is to make sure you confirm c is 0. Usually c will be 0. I'll give an example in one of these examples of how to do it. But yeah, that's what we covered so far. It's not too much, actually. It's honestly not that much. But now we're gonna get into some harder examples applying these, applying this, right? We got one example here, we got another one, and this one, that one's kind of just like a cool thing, but you can also try it at home. It's pretty cool. I'll just get into it. All right, let's take g at x is equal to arctan of x. Let's try to find the power series that represents arctan of x. All right, and now at first you can be like, what the hell do we do, right? But arctan of x is related to something like, let's say, we know we can write this as a series, right? This is just the geometric series, right? Can you relate these two in any way? And just try to go from there. But I'll give the solution. When we differentiate this guy, right? We end up with 1 over 1 plus x squared, right? This follows. And these are pretty close. In fact, we can define some f at x as this geometric series, because this is essentially just as if ck was 1 and a was 0, right? We can do this. And we also know this is equal to 1 over 1 minus x. So we know that g prime of x is actually just equal to f at negative x squared, right? Because this is equal to 1 minus negative x squared, right? So this is where your mind should go. And now this is solely computation, right? So we can just plug in negative x squared into here, right? So then we end up getting the infinite series of negative x squared to the n, right? And this is valid for all negative x squared less than 1. All right, which is the same as saying x squared less than 1, which is the same as saying x less than 1. Okay? Like, yeah. So this is all valid on the same domain as this guy. Okay? And we can rewrite this guy as negative 1 to the n times x to the 2n. Okay? And now we know this is equal to g prime at x. But that's not what we want. Okay? We want g of x. This is where integration plays in. Remember, we can integrate it, and the radius of convergence won't change, right? So let's just do that. Let's integrate this guy. And now we end up with g at x plus c is equal to this guy. And when we integrate it, we only integrate the x term, right? The integral of x to n dx. And this is just equal to, because 2n is just some number, right? This is x to 2n plus 1 over 2n plus 1. Great. And now how do we figure out c? Okay, well, let's just plug in 0. Let's plug in x equals 0. G at 0, which is arctan of 0, is 0. So g at 0 plus c is equal to c, right? This is equal to the infinite sum of this guy, which is 0. So c is equal to 0, right? We see how we got that, right? So then we can conclude, we can represent g at x, which is arctan of x, as the infinite series of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Boom! That's the solution. And this is probably full marks. I mean, I don't know. No, the TAs might just be like 1 mark, but yeah, there you go. The next example we'll do is a bit harder, but also equally important. Let's have g at x equal to x squared over 1 minus x squared. Try to figure out how to represent this in some power series. Oh, sorry, an infinite series. Now, I'll just do it. when you have something like this, right, your first instinct is probably to try to cancel out the top term to 1, right? Like maybe let's have u is equal to x squared, right? And that was where my first inclination went to. But these guys are easier than you think. Because when you represent something with an infinite series, right, you're just plugging in numbers, right? You're just plugging it in. You don't need it. I think we're conditioned too much to think about like power, like product rule and quotient rule. You don't gotta do all of that. You can literally just have this as x squared times 1 over 1 minus x squared, right? And now, this guy, right? Let's rewrite f at x as the geometric series, yeah? This guy is related with that guy. Do you see why? The derivative of f at x is equal to that. Right? So this is equal to f prime at x. Meaning that this is equal to x squared, and f prime at x, right, is just the derivative of this. Right? F prime at x is n x n minus 1. So we can write this as an infinite series of n times x n minus 1. And then now we have this x squared, right? And if we imagine this infinite sum, all right, let's do a quick show. All right, let's just convince you why this is possible. Let's have this multiplied by the geometric series first, right? This is equal to x squared times 1 plus x squared plus x cubed plus blah, blah, blah. And then this, you multiply into each term, right? So this ends up equaling x squared plus x cubed plus x to the 4 plus blah, 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 right? Meaning that you can just straight up just, plug in, like you do this. Like you can bring this guy in, you can open the door and just go in. That's why these series are actually really easy to work with, so long as you know the rules that you're allowed to do, right? So this is just equal to n times x to the n plus 1, right? Because this is, we can rewrite this as x squared, and then this is the same as adding 2 over here, right? So this becomes this, and this is the series. That's how g of x is represented, right? And we know this is the case. Like when we plug in f prime at x, that's true for all x less than 1. All right, so this is all true for x less than 1 as well. Because when we differentiate this guy, nothing changes, right? The radius of conversion doesn't change. All right, in this last example, it's very, very challenging to see. So if you can see it, it's very impressive. But this is more of like a cool, very cool application of this stuff. So let's take the alternating harmonic series, right? And we can write it, so there's 2 ways to write it. We can write it like this, right? Or we can also write it like that, okay? Either one is the exact same, right? Sorry. We can write it, or we can write it like this. Yeah. This or this, because either way is alternating, right? Let's find the value of this. And, okay, I'll give you a spoiler alert. This is equal to ln 2. Okay, that's the answer. Can you solve it using the things we've learned here? Here's a hint to start. Define f at x like we always have as the geometric series. Okay. X equals 0 negative. X to k. And then see if this can lead anywhere. Right? How can you get this closer to this? And I'll go through the steps. It's not very intuitive, but it's a very cool application. Let's look at f when you plug in negative x. Okay? When we plug in negative x, we get 1 over 1 plus x, right? Which is equal to the infinite sum of negative x to the k. Okay, and this is equal to, we can factor out the negative 1 and x to the k, right? This is all fine and dandy, right? And this is actually, you know, we're getting closer to here, right? Because we have the negative 1. And if we can figure out this is, you know, what this value is at x equals to 1, then we figured out this, minus the 1 over k, right? So how can we get that 1 over k? Like, how do we get to that? Well, we can see that if we were to integrate this guy, hypothetically, right, we could get something over k plus 1, yeah? Which is pretty close. So let's do that. Let's try that out. Let's say the integral of f of negative x is equal to the integral of this, right? Which is equal to this. This would be a xk plus 1 over k plus 1, right? And now we can see we're really close. We're really close, right? And we also know this is equal to the integral of 1 over 1 plus x, okay? Because we know this, right? So we're getting close. And now we can actually rewrite this sum. All right, this is something that's pretty cool. We can rewrite this sum because our k's are different, right? Our k is different. So how would we rewrite this sum in respect to it starting at k equals to 1? Well, let's see. If we shifted everything 1 to the right, right? We got to shift all of these k's 1 to the left. So now we get negative 1 k minus 1 times x to the k minus 1 plus 1 minus 1, which cancels to just k, over k minus 1 plus 1, right? Which is just k. And would you agree that k minus 1 is the same as k plus 1, right? Because minus 1 multiplied by itself alternates for every like even and odd number, right? Meaning that minusing 1 and plusing 1 end up with the same number here. So we can write that as k plus 1. Now, wait a minute. This is the exact same as this, except when we evaluate x is equal to 1, right? And we know the integral of this is ln of 1 plus x. Look at that. And now this is what we do. We can't exactly just plug in x equal to 1 here because we don't know this is conversion at 1, right? Now, or I guess we do because ratio test. But the better thing to do is to take the limit as x goes to, I guess it'd be 1 from the left of this. When this is equal to our alternating series, right? And then if we take the limit as x goes to 1 from the left of ln of 1 plus x, this guy doesn't care. This guy's defined no matter what. This guy is ln 2. And so this is our sum, meaning we just proved that this is equal to ln 2. And I think Alfonso had a video showing this, I think. I don't know, I forget. But this is a way to prove it, and I think that's pretty cool. And that's 9.1, so it's kind of long. Alfonso kind of rushed through all of this in like a few videos. And I didn't even cover everything, right? I skipped the proofs. But yeah, that's 9.1. So this is all power series. And the next video, I'm going to do Taylor polynomials. And yeah, I haven't learned that yet, but I'm sure it'll turn out fine. But yeah, that's the video. I guess I kind of recorded for a decent long time. That was almost an hour. I hope this is a good review. And yeah, the text was actually pretty useful for this. The proofs are stupid, but I just ignored the proofs because I don't think 1 through 7 we'll actually look at the proofs too much. But yeah, that's the first part of Unit 14. There you go.